Yesterday I was telling you about projective spaces and lines and planes and so on in projective spaces, and we looked at a fairly simple proof in projective geometry. Today we're going to look at a slightly more complicated theorem, which is Desargues Theorem. So this is not really the main focus of the course, but it's a way of getting you into projective spaces and projective geometry. So the statement is, so I'm going to write my points with capital letters, and then later on I'll have small letters for representatives of the points. So big P, big Q1, Q2, Q3, and R1, R2, and R3. These are 7 distinct points in a projective plane. That's over any field. So such that the lines Q1 R1 and Q2 R2 and Q3 R3 are distinct. They're different lines and concurrent, meaning they all pass through the same point at big P. So incidentally, in a projective plane, if you have 2 distinct points, there's a unique projective line passing between them. What you do is you take representatives as the points in the overlying vector space. Those 2 representatives span a 2-dimensional vector subspace. The projective space of that vector subspace is a projective line, unique projective line containing those 2 points, just like in R2. Okay, so continuing, if we let big S1 be the intersection of the lines Q2, Q3 and R2, R3. These lines, well, any 2 lines, if they're distinct, have a unique point of intersection, and S2 is the intersection of the lines we're going to cyclically permute, so Q3, Q1 and R3, R1. And S3 is the intersection of the lines Q1, Q2 and R1, R2. So we're cyclically permuting 1, 2 and 3. So that's all the hypotheses, and the conclusion is that then S1 and S2 and S3 are collinear. So I'll have a go at drawing a picture on the board. It's not an easy picture to draw. If you've got a ruler, it might be easier for you, and you can treat that as an experimental test as to whether the theorem is true or not. You draw all these lines, and then in the end you have to know are S1, S2, S3 in a line or not. So let's see if I can draw something vaguely sensible. So here's my point P, and these are my 3 lines. And let's say I want something like a Q1 there, and a Q2 there, and a Q3 there. So I can draw the lines Q1, Q2, and Q2, Q3, and Q3, Q1. And oh dear, let's also have points Well, let me try. Let's try and make that the line R1, R2, R3. So this can be the point S2, that can be the point S3, and that can be the point S1. And now let's draw a line a bit like this. So that's going to be my R3, that's going to be my R2, and a line like this. And that can be R1, and a line, I'll go up. Okay, so some of those lines don't look terribly straight, but here's the line P1, Q1, R1, P, Q1, R1, there's a line P, Q2, R2, there's a line P, Q3, R3, this is the line Q2, Q3, and so on. And the claim is that when you draw all those lines, that they end up determining 3 points S1, S2 and S3, and those 3 points should be on this red line. All right, so let's now prove this. We have all these points in the projective plane. Let's call this projective plane P of V. And we're going to choose representatives for them, non-zero vectors, which are kind of bases for these one-dimensional lines, representatives for them in the vector space big V. So we're going to choose representatives small p, small q1, small q2, and so on, etc., for the points big P, big Q1, big Q2, and so on. And these are in the vector space big phi for these points in the projective space P of V. The representatives are not unique. You're free to rescale each of these by some non-zero number in your field. Okay, so as big P and big Q1 and big R1 lie on a line, so little p and little q1 and little r1 are linearly dependent. So these 3 points line a projective line, therefore those 3 points line a two-dimensional vector subspace of big V. And as the three of them, there has to be some equation between them. So by rescaling the Q1 and the R1, but not the P, we may ensure that the way I want to write it is P is Q1 plus R1. Okay, so what's going on here is, well, first of all, we know that something like lambda P plus mu Q1 plus nu R1 is 0. I claim that all of those constants, lambda, mu and nu, are all non-zero, because otherwise two of these things would be proportional, which would contradict the points being distinct. So we have some relation of the form lambda p plus mu q 1 plus nu r1 is 0. We can divide by lambda and put p on the left-hand side. We get p is something times q1 plus something else times r1, where the somethings are non-zero numbers in your field. You then replace the q and the r by those multiples of them, because we're free to rescale them, and we can, sorry, is that, yes, it was, and then we can get that equation. Okay, but I've chosen not to rescale p because I'm going to do the same thing several times, and I don't want to. Okay, so then, and similarly, p is q2 plus r2, and p is q3 plus r3. So I'm taking my initial choice of p to be fixed. There are then unique rescalings of the q's and the r's to make these three equations true all at once. Okay, so the magic of this proof is we're using the freedom to choose representatives of the points up to scale in the overlying vector space to make equations hold in that vector space. So, as little p is q2 plus r2 is also q3 plus r3, we know that we can subtract, and q2 minus q3 equals r3 minus r2 equals, let's call that vector s1. Okay, so for the moment I'm just defining little s1 to be that vector. So since big Q2 and big Q3 are distinct, then little q2 minus q3 is non-zero. Because otherwise, if they were equal, if it was 0, they'd have to be the same point. So hence, little s1 is a representative of a point on the line q2, q3, because it lies in the two-dimensional vector subspace spanned by q2 and q3, and the projective line of that is the line q2, q3. Okay, and similarly, but S1 is also R3 minus R2, so S1 represents a point on the line big R2, R3. Okay, so thus little s1 represents the point big S1, which is defined to be the intersection of Q2, Q3 and R2, R3. Okay, so we can choose a representative for S1 which has these nice relations. So similarly, just cyclically permuting the 1, 2 and 3, we can put little s2 is q3 minus q1 is r1 minus r3. Little s3 is q1 minus q2, which is r2 minus r1. And then little s2 and little s3 represent big S2 and big S3. But now we get the payoff, which is that S1 plus S2 plus S3 equals brackets Q2 minus Q3 plus brackets Q3 minus Q1 plus brackets Q1 minus Q2. And of course everything cancels, and that gives you 0. So those 3 points are linearly dependent, Therefore, and in fact they are also distinct up to scale, so they generate a two-dimensional vector subspace of our projective plane, or of our vector space, not a three-dimensional vector subspace. So they lie on a line. So hence, big S1, and big S2, and big S3 are collinear. Well, I suppose, if you like, they're in the line P of the span of S1, S2, and S3. Well, that's two-dimensional. So as little s1, little s2, little s3 are linearly dependent. So that finishes the proof. Any questions about that? No? Everyone understands everything? Right. Let's move on to our next topic, which is projective transformations. So these are special kinds of maps between two projective spaces. So let big V and big W be vector spaces of the same dimension, or the same finite dimension, over the same field F, and let big T going from B into W be an invertible linear transformation. So an isomorphism of vector space. So we're going to use this to define a transformation from the projective space of V to the projective space of W. So if a non-zero vector little v lies in big V, then T of square brackets V is square brackets TV. So square brackets V is the one-dimensional vector subspace of big V. I then apply T to that. I get a subset of W, which is just the one-dimensional vector space spanned by the point TV. So where brackets V is a vector subspace of V, of dimension 1, and brackets TV, a vector subspace of W. And then as T is invertible, so TV is non-zero, and this point square brackets TV is a point in the projective space W. So hence big T induces an invertible map, which we'll call tutor, Greek T, from big P of V into big P of W by tutor of square brackets little v is square brackets big T of V. And that's true for all non-zero vectors little v and big V. And this is well defined, that is, it doesn't depend upon the choice of representative little v in here. A different representative would scale by a number, and then as t is linear, that would scale by the same number. Okay, and we call this map tutor a projective transformation. Okay, so you might think that requiring big T to be invertible is a bit strong. So you can define linear maps without requiring invertibility. In fact, we can define tutor going from P of V into P of W if the linear map big T is only injective, not invertible. But if big T is not injective, then tutor is not defined on the subset P of the kernel of big T of P of V. So if V is a non-zero vector in the kernel, then TV takes it to 0. There's no point in P of W to which you could sensibly map a point of P of ker T. So we don't get projective transformations induced by general linear maps, only injective linear maps, and it turns out that basically the ones we care about are things coming from invertible maps. Okay, so if lambda is a non-zero element of your field F, then the linear transformations big T and lambda times big T define the same projective transformation little tutor, because square brackets lambda t times v is the same thing as square brackets t times v for some vector little v. And when big V is big W, the projective transformations tutor going from P of V into P of V form a group under composition and it's sometimes written or PGL of big V or let's say PGL of n plus 1 acting on Cpn, which is P of C to the n plus 1. Or sometimes PGL n plus 1 comma C. So PGL stands for projective general linear, whereas T would be an element of the general linear group. Right, so let's look at an example. In the simplest case of dimension 1 projective spaces, let's relate this to something you hopefully already know about from complex analysis. Well, let's look at the complex projective line. CP1 is P of C2. So this can be written as CP1 is, well, let's split it up as points of the form 1, z for z in the complex numbers, together with the point 0, 1. And we identify the point square brackets 1, z with the complex number z in C, and we write 0, 1 as the point infinity. So then, this is the inhomogeneous coordinate on, well, the kind of U0 in CP1. And this is the point at infinity, which is only one point in this dimension. So then, well, CP1 is identified with, or isomorphic to, the complex numbers together with the point infinity, which is known as the Riemann sphere from complex analysis. So it's a one-point compactification of the complex numbers and meromorphic functions, which are holomorphic functions allowed to take the value of infinity, map to here. Okay. So now let Tor going from CP1 into CP1 be a projective transformation induced by a linear transformation big T going from C2 into C2. Okay, so I'm going to write my action in a slightly funny way in order to reproduce the conventional notation in complex analysis. So let's write the action on Z0, Z1 in C2 as big T is going to map the column vector Z1, Z0 maps to A, B, C, D times column vector Z1, Z0. Okay, so I'm doing something slightly strange there. I'm writing my column vector upside down. If you want to write it the right way up, then you have to kind of turn this matrix inside out and do probably DCBA or something. Nothing profound about that. I'm just doing it to get the usual expression for Mobius transformations, which is about to appear. Okay, so this is the column vector A Z1 plus B Z0 and C Z1 plus D Z0. So therefore, the induced projective transformation, Tor, takes square brackets Z0, Z1, maps to square brackets c z1 plus z0, so a z1 plus b. Sorry, left out a d there. Okay, so why have we done it like that? Well, let's take the case that if z is a complex number and cz plus d is non-zero, we have that tour of square brackets 1 comma z, so I'm putting z1 as z, z0 as 1, is equal to, well, it's a cz plus d comma az plus b, but I can divide by the cz plus d and then write that as 1 comma az plus b over cz plus d. And the only reason for turning my my thing upside down is that if I'd done it the other way, I would have got c plus dz over a plus bz, I think, or something like that. Okay, so therefore, in the inhomogeneous coordinates, in other words, the kind of c together with infinity representation, we have that tour of z is, well, there's three possibilities. We can get az plus b over cz plus d. That's the main case when z is in the complex numbers and cz plus d is non-zero. There's two other cases. We can get infinity if cz plus d equals 0. That's because then, then that's 0, that's non-zero, so it's the point 0, 1, which we're identifying with infinity. And then the third case is that you can get a over c if z equals infinity. That is, if instead you take the point 0, 1 here, then you get a there and c there, so you divide it out, you get a over c. Okay, so this is hopefully familiar. So this is the so this is a Mobius transformation from complex analysis. So Mobius transformations are the holomorphic isomorphisms from the Riemann sphere to itself. So hence, projective transformations of CP1 are the same as Mobius transformations. And in high dimensions, projective transformations, you can think of them as generalizations of Mobius transformations. Any questions? All right. let's now move on to our next topic, which is something called points in general position. Yeah?
Sorry, why do Mobius transformations have to be of a complex plane instead of just any field in general?
Well, yeah, they do make sense over any field.
Oh, okay.
It's just that I'm hoping you have met them
Yeah.
in the context of complex analysis and holomorphic functions.
Thank you.
Okay, so we know that for a finite dimensional vector space, the concept of a basis is very useful. And a basis in an n-dimensional vector space is a choice of n vectors satisfying some non-degeneracy conditions, if you like, linear independence. So points in general position, it's kind of an analogue of bases for projective spaces. But perhaps surprisingly, for an n-dimensional projective space, we're going to need n plus 1 points to form this basis. And we'll get to explaining why we do this at some point soon. Okay, so let big V be a vector space of dimension n plus 1 over any field, and big P of V, the associated projective space of dimension n. So let's take little p0, p1, all the way up to pn plus 1. So total n plus 2 points, numbered from 0 up to n plus 1. Let these be points in big P of V, and let little v0, v1, up to vn plus 1 be representative vectors in the vector space big V for the points p0 up to pn plus 1. So these are only unique up to rescalings by non-zero elements of your field. So let's make a definition. So we say that the points p0 up to pn plus 1 are in general position if, well, there's two equivalent conditions. Firstly, no n plus 1 of the points v0 up to vn plus 1 are linearly dependent or equivalently to no n plus 1 of p0, p1 up to pn plus 1. No n plus 1 of these lie in a hyperplane. So, in case you've forgotten, a hyperplane is a projective linear subspace of P of V of dimension. The dimension of big P of V minus 1, well, which is n minus 1 in this case. Okay, so let's note that this is an algebraic condition. It's about linear algebra, linear dependence of vectors, whereas this one is an equivalent geometric condition. It's about points lying in planes and things. Well, it's, if you want to see that well, to see that 2 implies 1, if n plus 1 of these guys lie in a hyperplane, then n plus 1 of their vectors, their representative vectors, lie in a subspace of dimension n minus 1, dimension n rather, of V, which is the vector space lying over the hyperplane. So then n plus 1 of those representative vectors have to lie in a vector space of dimension n, which forces them to be linearly dependent. Conversely, to see 1 implies 2, if n plus 1 of these guys are linearly dependent, then those n plus 1 things span a vector subspace of V of dimension less than n plus 1. So you choose a vector subspace of V of dimension n containing the vector subspace spanned by these guys, which has dimension less than or equal to n, and projectivizing that gives you a hyperplane containing the corresponding points here. Okay, so these two conditions are equivalent in a simple way. So the word general kind of means not special. And let's say if you're working over the complex numbers or the reals, it means it's a generic condition. That is, if you choose n plus 1 points at random, then with probability 1, it will satisfy this condition. It means that special things don't happen, like some subsets of the points lying on a line or whatever. So just as examples, if n equals 1, and P of V is a projective line, then 3 points are in general position if they are distinct. Whereas when n equals 2, the P of V is a projective plane, then 4 points, so n plus 2 is now 4. 4 points are in general position if no 3 of them are collinear. In this case, you don't want 2 points to lie in a hyperplane, but a hyperplane is in a projective line is just a point. So 2 points lying on a hyperplane means 2 points being the same. Not lying on a hyperplane means being distinct. For projective plane, a hyperplane is a line. So you want no 3 points to lie on a line, no 3 of them to be collinear. So So a situation like this is good, whereas a situation like this is bad, because those three lines those 3 points are on a line, and various of these lines have collapsed onto that one. Okay. So, well, there's one theorem in the course about points in general position, which we'll now state. I think we'll prove it next time. Okay, so here is the main result on points of general position. So it's a theorem, and I'll give it the number 1.1. So I can refer to it later. Okay, so let big V and big W be vector spaces of dimension n plus 1 over the same field implicitly. We don't care what the field is, this is true for any field. And let little p0, p1 up to pn plus 1, and little q0, q1 to qn plus 1 be in general position in big P of V for the p's and big P of W for the q's respectively. So then there exists a unique projective transformation tutor going from P of V into P of W with tutor of Pi equals Qi for I is 0 up to n plus 1. Okay, so essentially projective transformations are they can act sort of transitively on sets of points in general position, if you like. So the proof can be next time. So I've got time for a couple of comments about this. Well, any questions about the statement? So just a remark. So if V and W are vector spaces of dimension n, and V1 up to Vn and W1 Wn are bases, then there is a unique linear transformation big T going from V into W with T of Vi equals Wi. So that's a very similar statement to that. And so points in general position are a projective analogue of a basis of a vector space. So that's one remark. A second remark is a dimension count So let's say in Cp to the n, say, well, so points in general position basically form some open subset of Cpn raised to the power of n plus 2. So that is that I've got n plus 2 points in here, and the dimension of the set of points, or set of sets of points in general position, is the dimension of this space, which is n times n plus 2. So you need n plus 2 numbers to describe a general point in there. Now, projective transformations of Cpn are, well, it's really GL of n plus 1 C divided by C star. So these are square matrices of dimension n plus 1, or n plus 1 by n plus 1, and this is really one-dimensional complex numbers. So that's got dimension n plus 1 squared. That's got dimension 1. So the dimension is n plus 1 squared minus 1, which is again n plus 2. So, so that's consistent with the fact that this group acts freely and transitively on this set. That's a kind of consequence of the theorem. So we have a group of that dimension acting on a space of that dimension, and actually these two spaces are the same. So that's a kind of sanity check for this theorem. All right, let's call it a day there. Reminder, no lectures Wednesday and Thursday next week. The lectures will be on Friday between 11 and 1 o'clock in L3.